Well, okay, please try your best to keep yourself mute as well. So, Dr. Eyitayo has a MSc degree in structural mechanics and a PhD in civil engineering from New Zealand. He has extensive research experience in proof load testing of bridges, laboratory testing of full-scale structural components, and nonlinear modeling of concrete structures under various extreme loads. He's currently involved in various international research projects on vulnerability of civil infrastructures in Canada, the United States, Indonesia, and New Zealand. He's a member of American Concrete Institute subcommittee working on ACI 369. That's the one for seismic repair and rehabilitation of concrete buildings. Dr. Eyitayo, we're very honored to have you here. Whenever you're ready, please share your screen.
Thank you, Arash. I will share my screen now. Yeah. All right.
Perfect. I can see your screen.
Yeah, presenters mode, right?
Yes, perfect.
Yeah, cool. All right.
Oh, yes.
All right, cool. Thank you. Hello, everyone, and welcome to this seminar. I'll be talking about seismic assessment and nonlinear modeling of structures with splice deficiencies. So I will be talking about as built as well as rehabilitated structures. The outline for the seminar is split into 5, and I'll actually be talking, giving an overview on components with splice deficiencies, then talking about the experimental as well as field evidence on the seismic behavior of components with short splices. Then I'll give a bit of background on existing numerical modeling approaches, the approach which we've proposed for assessing this component, as well as talk about applications to buildings. I would have loved to talk about applications to bridges as well, but because of time, it's important to basically keep it as short as possible. So I will mostly focus on applications to buildings. However, majority of what I'll be talking about today is applicable to both buildings and bridges, and we've actually carried out the studies on this. So when we look at other type structures, there are lots of vulnerabilities which we actually find in these other type structures, and that has to do with the fact that prior to the 1970s, our knowledge about seismic vulnerability was quite limited. So you have issues like having short splices in the plastic hinge region of components. So here is actually a case whereby you have a short splice and you can actually see the poor confinement around the splices. And this is really a timeline of how the American Building Code really treated the minimum splice length in concrete components. And you can actually see that for a long time, you can actually have splices as short as 25 dB, which is 25 times the bar diameter in concrete components, which of course would typically lead to some form of bond deficiencies if you're going to actually have some form of splice failure or whatnot. So in terms of what past events have taught us, we can actually see that in bridges, you can have some form of very strong pull-out failure happening, which really leads to like the collapse of bridges. And in buildings, there are evidence of significant deterioration of the plastic hinge region of components with short splices. So, of course, when we go to experimental test results, we've been able to really look at tests that have been done in which the components are either dominated by shear mechanisms or dominated by a bond failure mechanism. So, of course, a shear dominated column is one in which you actually have this critical diagonal failure plane forming. And in the bond controlled, you tend to be dominated by a fixed end rotation. So in this lecture, in this seminar, I'll actually be talking a lot about shear controlled, bond controlled, flexure controlled. So just to really give people a bit of background about what this means. So the response of a concrete column, beam, or walls is dependent on 3 deformation components. So you have the flexural component, which is pretty much due to flexural curvature. And you have the shear component, which is mostly due to shear distortion. And then you have the fixed end rotation, which can actually be due to bar slip or some form of bond loss in the component. So depending on the failure mode you have, one of these three deformation components would actually dominate the response of your column, your beam, or your wall. So for bond-controlled columns with short splices, what actually happens is, as you can actually see on the plot, this is a hysteresis plot of a test that was carried out at UCLA sometimes back. And what you actually see here is that the bond failure actually happens at a drift of about 1.5%. And of course, you can actually see how the degradation is very fast. It's quite sharp. But interestingly, the column doesn't suffer axial failure up until a large drift of 7%, which is quite high. But what is quite interesting about this is the fact that you can see the very significant pinching behavior, and you can also see the thinner hysteresis plot, hysteresis loop, which is quite different compared to what you would get when you're looking at a code conforming column. But I mean, this behavior is actually associated with the fact that once you have a splice failure here, the component, the column, the failure mechanism transfers into more of a rocking type behavior in which you've lost the concrete rebar bond and the column is just rocking about its base and behaving like a semi-rigid block, which is rocking about its base up until you have significant crushing at the compression toes. And that is pretty much when you get to this point. So being able to capture the splice failure, the rocking mechanism is quite important in being able to develop a backbone curve to model this behavior, as well as develop the hysteretic parameters to capture the cyclic response of this component. So a bit more of experimental background. So I like to basically back up everything what I say with experimental results. And here is the plot showing the base moment versus rotation for the column, which I just previously showed. And what we actually see is the fixed end rotation is actually contributing about 80 to 90% of the total rotation happening in the column. And like I said, it's actually due to the bond loss, which actually happens. So in reality, if you're trying to model this type of column, you need to ensure that you're basically capturing this fixed end rotation as much as possible, because you'll be getting lesser of deformation due to flexural curvature, and you'll be getting lesser of deformation due to shear distortion. Another thing to also think about is the fact that based on the strain gauges that were put on the bars in this column, what happens is, because you have the bond loss, which happens before your yield strain, you don't develop enough tensile stresses in these bars, which means they never actually yield throughout the test. And it's quite interesting that at about 3%, you still don't reach the yield strain. And that is an evidence to support the fact that this component actually experiences rocking mechanism without the contribution of the longitudinal bars, because they are not really taking up any tensile force. So this is a plot that you should all be familiar with, I guess. And it actually shows the type of numerical modeling approaches that are available for capturing the response of structural components. But of course, what to actually really think about here is the fact that you could actually use any of these approaches to model the response of your component. But it's important to really think about the criteria for selecting the technique. And of course, the things which we tend to think about are the reliability of the approach which we are using, the practicability of this approach that we are using, as well as computer efficiency. So I've put computer efficiency in asterisks, and that is because in 2022, computer efficiency is not really so much of a big deal because of the computational power that civil engineering companies and researchers have in stock. So it's not really much of a big deal. But of course, another confusion which tends to happen is a lot of people tend to think that complexity is quite equivalent to reliability. But of course, what we've actually learned is that the complexity of a model doesn't mean it's more reliable, because what is important is you're able to actually capture all the deformations you're meant to get, and what you're capturing is in the right proportion. So if your model is assuming that you're going to get a 40% contribution of flexural curvature, but in reality, you're going to be getting 90% contribution of curvature, flexural curvature, then something is going to be wrong. I mean, depending on what you're trying to capture, but it's left for you as an engineer or as a researcher to first identify what you're trying to capture before you then decide on what you're trying to model. So naturally, or research-wise, not naturally, what happens is for each of these components, there are various techniques to actually capture the deformation response. So for the flexural component, you actually use a fiber element section, or you can use a flexural spring. So the flexural spring is actually basically converting from a moment curvature into a moment rotation and putting all that characteristics into a spring to basically capture the flexural response of the component. While the shear component is basically using a shear spring and defining a shear force versus shear distortion type of plot to then capture the response of the shear spring. And then you have the fixed end rotation, which is actually captured using a bond slip spring, where you define a moment versus slip rotation type of relationship. So depending on what you're trying to capture, typically what you do is you can aggregate either 2 or all 3 of these springs, or in some cases, you can lump all of them together into a single spring, which you can then use to basically capture all of this. And it reduces the number of layers of analysis that you're trying to really do at a single time. So it depends on how complex you're trying to go and what exactly you're trying to capture. So with regards to bond controlled columns, there are really 2 broad approaches that are being used to capture this response. And I'm just going to give a bit of an overview, but I've provided the references for these approaches for people that are really interested in finding more about them. So the first approach is typically, aggregating your flexural spring, your shear spring, and your bond slip spring. And then what you then do is you model the bond spring with the relationship that links your the tensile stress, the tensile force in your bar to some form of slip relationship. And then that is then transformed into a moment spring rotation, which is incorporated into your analysis. So you have some layers of analysis that are going on simultaneously to be able to capture the response of those components. Of course, for you to be able to use the spring, you need to assume that you're able to have some form of tensile stress, which is being passed across in your splices. But in reality, tests actually show you don't necessarily get that amount of tensile stress through your splice. So of course, in certain cases, the approach may not necessarily be applicable. The second approach is also quite a good approach in the sense that what you're doing is modifying the stress strain behavior of your steel. So instead of having a strain hardening law for your steel, what you're doing is once you pre-calculate when you're going to have your bond failure, and then you assume a drop in your stress in the bars at that point in time and provide a residual stress. So of course, if you're doing a non-linear pushover analysis, it's easy to basically adopt this type of approach in the sense that you don't need to really worry about how the hysteretic parameters are defined. However, when you're doing a non-linear time mixture analysis, it becomes of an issue of ensuring that the way you've defined your hysteretic parameters is quite the good approach. So, I mean, I'm not criticizing any of these approaches. It depends on what you're trying to capture, but they are both good approaches that you can use depending on what you're trying to capture. But of course, approach 2 can only be used when you are 100% sure you're having a bond control mechanism. It doesn't give you the opportunity of basically capturing shear failure. Although if you're trying to capture failure, you can also include a shear spring here, like it's done in approach 1. But of course, to do this, you need to really have a failure mode classification approach, which is really something I'm going to talk about shortly. So like I mentioned before, when you have a short splice, it does not mean you'll be bond controlled. In certain cases, you could actually be shear controlled. So it's important to be able to identify your failure mode first before you then decide on before you then choose on how to capture them, as well as ensure that what you're using to capture them is adequately doing the job. So what is typically done is using a strength-based approach in which you are comparing 3 strengths. The first strength is your shear strength. The second is your flexural strength, while the third strength is actually the lateral strength corresponding to the developable stress in your tensile splices. And of course, by comparing these strengths, you could actually decide whether you have a shear failure, a bond failure, a flexural shear failure, or a flexural failure. But of course, in older type columns, the likelihood of having a flexural failure is quite low, and that is because of the poor confinement you have around your bars. So for this strength-based approach, we actually have a data set of 29 column specimens. So there are a lot fewer tests that have been done on bond controlled, or basically columns with short splices in general. So we're able to basically use that data set to validate this failure mode classification approach. And of course, we're able to predict 27 out of the 29 specimens, the failure mode correctly, which is about a 93% accuracy, of course, which is quite good from a seismic assessment perspective of ensuring that you're able to predict your failure mode before you can evaluate the probable force displacement response. So prior to now, the two approaches which I've shown model the behavior of the different deformation components separately. But in the approach which you are proposing, the idea is you're actually lumping all of them into one single spring. And the idea is you're reducing the amount of time or the effort in defining various layers of analysis, which are not exactly the best in certain cases, and you're also increasing your amount of uncertainty if you're combining lots of formulations together in that regard. But lumping them together, all you're basically defining is your pre-capping rotation capacity, your post-capping rotation capacity, your residual strength, as well as some form of hysteretic parameters. So if you're doing a nonlinear pushover, you don't need to really worry about the hysteretic parameters. All you care about is basically the pushover. And of course, all you care about is the backbone. And of course, you define your acceptance criteria either based on ASC 41 type of approach for immediate occupancy, life safety, and collapse prevention, and you're done with your assessment. But if you're doing a nonlinear time history analysis, you obviously need to basically be able to capture the cyclic deterioration as well as the pinching behavior of this component. And I'm going to talk about that shortly. So to capture the pre-capping rotation capacity, here is a free body diagram of what a splice looks like when it's going through some form of lateral demand. So the splice has to actually transfer a tensile force T. And of course, to be able to transfer that tensile force T, there has to be some form of clamping pressure that is being applied by the stirrups around the splice. So if there are no stirrups around the splice, it's unable to transfer this force. So the equilibrium to this free body diagram actually happens based on the relationship you have between your tensile force as well as the clamping pressure that you have. So of course, if we link that relationship together, we can actually say that once you are unable to transfer this tensile force due to some form of reduction in your clamping pressure, you've exceeded your capping point. So the pre-capping rotation capacity can then be linked to this clamping coefficient, which is the ratio of the tensile force you're trying to pass across the slice and the clamping force which you have. So what we did was, we know this already, then how does that compare with experimental test results? So using the database that we had, we tried to work out the relationship between the clamping coefficient and the measured pre-capping rotation capacity. And you can actually see that at very, very low clamping coefficients, that is when you have more of the clamping force over the required tensile demand, your rotation capacity is quite high. But as soon as your tensile demands are quite high compared to your clamping force, your rotation capacity is very, very reduced. So this could actually be simulated using a simple relationship. But I must point out that this relationship actually doesn't account for the influence of axial load. So we basically looked at the model error in the previous equation that I showed, and we found out that the model becomes unconservative after an axial load ratio of 0.2. So you can represent that with an equation lambda, which is a multiplier to that equation, and that helps you capture the pre-capping rotation capacity of a column expected to be bond controlled due to short splices. So once splice failure occurs, like I mentioned, you transition into a rocking mechanism. So sometimes back, I developed a rocking model for capturing the rocking behavior of columns or plane bars. And the idea of the rocking behavior is that under lateral demand, the stability to the column is provided by the compression strut that is due to that comes from the axial load on the column. And this compression strut forms an angle alpha with the longitudinal axis of the column. So instability occurs when the fixed end rotation of your column is equal to the compression strut angle. And I won't really go into much details of the calculation, but the background is from this overturning angle, when you combine it with the expected flexibility you get in the column, as well as account for the crushing that will happen at the compression to lead to axial failure, you actually find out that the plastic rotation at axial failure for bond-controlled columns is mostly dependent on axial load, and pretty much because they are rocking. So the axial load is really the most important parameter. So anybody who is interested in looking at the way this formulation was developed, which is a mechanistic formulation, can actually check these references out. So we've adopted the same formulation, which was originally developed for columns or plane bars, and we basically adopted it for columns with lap splices that are bond controlled. And we actually see that it does a good job of predicting the response very well. So of course, the post-capping rotation capacity is the difference between the plastic rotation at axial failure, which we predict using this model, as well as the pre-capping rotation capacity. And that pretty much gives you all your deformation components. So the last parameter which you need for your backbone is your residual strength. So we took a bunch of data in which of tests that were tested to very, very large drift demand, such that there was significant deterioration in strength. And we pretty much found out that we can represent the relationship between the residual strength and axial load with a simple linear relationship, which is shown here. And it does a good job of predicting the residual strength of bond-controlled columns. So using the strength and as well as deformation components, which I've talked about, you can basically create your backbone. So for a nonlinear pushover analysis, like I talked about, all you need is the backbone. But if you're trying to model the hysteretic behavior for a nonlinear time history analysis, I would actually recommend using this backbone with a modified IMK pinching material, or maybe a pinching no for material, which are actually available on Opensees. So I can basically talk about the two materials, how the hysteretic parameters are defined, but due to time, I'm actually going to talk about only the IMK pinching material. For the IMK pinching material, the cyclic strength and stiffness deterioration on lander is actually, we found out that it wasn't really so much dependent on axial load and transverse reinforcement ratio. Of course, it's hard to tell because we don't really know if it's due to lack of data, and it's possible that this lander factor should actually deteriorate with axial load. But I mean, there are a couple of experimental tests that are being done to really fill up this gap, and we hope to really know that. But for now, what we're basically proposing is assuming that your lander is a constant value. But for the pinching behavior, kappa, we have proposed using a kappa value with a modified IMK model that is actually dependent on the transverse reinforcement ratio, and that actually helps you capture the hysteretic behavior of this component using the IMK pinching model. So when we compare that to experimental tests, we actually are able to predict the cyclic behavior of this component. So this has been validated with about 26 test specimens, and it does a good job of actually capturing the nonlinear behavior of this component. So that is that about modeling bond-controlled columns. But like I mentioned, there are columns that would be shear-controlled as well. So I've spent a bunch of my life talking about shear-controlled components, so I wouldn't really go into much details. And so, but I will just give a bit of an overview because it's not really the main focus of this discussion. But if you have a flexure shear mechanism, for example, in which you are expected to have some form of flexural yielding, after some point, you can actually hit the shear limit curve, and that results into a shear failure happening. And immediately the shear failure happens, the deformation path transforms into this red line, in which, you know, the column can still keep on carrying its axial load up until a point whereby, you know, it hits the axial limit curve and suffers axial failure. But of course, that part is actually based on a shear friction mechanism along the diagonal failure plane. And as much as it's straightforward to basically explain like this, it's important for people to actually see what it looks like from an experimental point of view. So here is a test that I did during my PhD, and expect to see the shear failure happening at the top of the column. And you can actually see where the diagonal failure plane forms. And at the end of the day, you actually see how excited I was about this column. And that is actually going to come. Yeah, so that was me during my PhD, and I'm easily excited when columns are failing in the lab. That is actually what I like doing the most. So I won't really talk about this model because I didn't develop it. It was developed by my PhD supervisor. And the idea is you can actually capture the shear behavior and the axial failure using a shear spring and an axial spring, which are connected in series. And of course, like I mentioned, you have the shear limit curve and the axial limit curve, which are then able to really capture the response. It's quite a very straightforward process. So I wouldn't really be spending so much time talking about it due to the time that we have. But I'll actually talk a bit more about the retrofitted cases. And the idea of retrofitting a column with splice deficiency is to actually provide an extra clamping force from either jacketing or from having a wrap around it. And what we've actually learned from past tests is if you actually design a retrofit properly, it's actually comparable. The response is comparable to a code conforming column. However, there is an issue that needs to be thought about properly. Is do we actually change our mechanism, or what actually changes? So even though the backbones are quite similar to a code conforming, what do we know about the deformation component? So a good example I like to really talk about is this test that was done in Canada to actually fix some of the bridge piers in Canada using ultra high performance fiber reinforced concrete. So what happens is using this HPFRC, they were able to really improve the bond behavior. However, what happens is while it takes away the splice failure, it still doesn't stop the bond, the deformation concentrating at the interface. And that actually gives us the perspective that you don't change your dominating component, but what you actually change is the energy dissipation capacity. So your bond component is still the dominating bond component is the dominating deformation component, sorry, is still bond slip, but the hysteretic dissipation capacity of that deformation component is improved by increasing the behavior of the coming from the HPFRC. Now, here is something to then think about when you're trying to model this component. So here is from a test specimen. It actually shows you that the curvature is concentrated at the column base, which means you don't get a spread of deformation across the column in terms of damage, you know. And this is the idea of having a fiber element section type of modeling approach, in which you're looking at your spread of deformation to actually be due to curvature spread across the height of the column. But what you're saying is that it is not the case. And what happens here is that your spread of plasticity is actually due to bond slip. So strain penetration into the column as well as into the column footing is actually a way in which this column experiences spread of plasticity. So like I said, you are able to really have this very, very nice looking force displacement plot, but it's important to really factor in the fact that it is still bond slip that is dominating. So if you're using a fiber element, you need to really ensure that the fiber element is really capturing what you're intending to capture. So Another interesting way to capture this is something which I did during my PhD. And of course, the idea is basically developing an IMK hinge type of model to capture this. And to do that, you basically look at the sleep that happens at the interface. And if you integrate the sleep by looking at the at the strain penetration length, and assuming a strain hardening law for your bars, you can actually work out the amount of plastic rotation that you need given a slip at the interface. So in this case, you are lumping all your deformations into that interface. And given the fact that test results show that 80 to 90% of the deformation is at the interface, there is actually no problem doing that. So if you combine this with a moment curvature type of analysis, you can actually go from a curvature into this type of hinge relationship in which you have like a moment versus rotation type of properties that can be used in your IMK hinge. And then of course, like I've been saying previously, if you're doing a nonlinear pushover analysis, all you can think about is basically just using this force displacement, using this moment rotation relationship. You don't need to worry about the hysteretic parameters. But if you're worried about hysteretic parameters, there are already formulations developed by Hilton et al., which actually helps you capture the behavior of some of these components. And when we combine this moment rotation plot with already existing hysteretic parameters, we are actually able to capture the relationship or the behavior of these components, which is actually a good thing. So before going into the building level, one thing people need to really think about when modeling is actually the variation in capacity at column ends. And that comes from the fact that you hardly have your splices at both column ends. So if you're having your splice at the bottom end, you need to actually understand which of the ends is actually your weaker region. And that is potentially what is going to dominate your behavior. So an example of that is this interesting test by Abraham Lin, in which the top part of the region of the column was designed to suffer a shear failure, and the shear failure was actually weaker than the lateral strength corresponding to splice failure in where you have the splice. And you actually see that the shear failure is actually what governs. But what I've actually seen in past studies is people have actually modeled this column as being bond controlled just because of the presence of the splice in the plastic hinge region. So this is really something one needs to be careful about as an engineer to ensure that you're able to capture the variation in capacity at your column ends in your model. So I'm going to basically rush through the building part of it. Sorry, because time is far spent. So to demonstrate the applicability of these models, we looked at various archetype structures, some of them 6 archetype structures actually, 2- and 4-story buildings, which were bond controlled, shear controlled, and we also looked at FRP retrofit. So we developed a nonlinear model for these buildings using Opensees, use the calibrated hinges in capturing the behavior based on assumed reinforcement detailing for the columns and the beams as well as the joints. And here is actually the pushover curves for the 2-story archetypes. And you can actually see that even though the bond controlled building starts degrading faster than the shear controlled, you actually see that it's able to really carry on majority of its gravity load and majority of its lateral demand up onto a very large roof drift. And that is as a result of the fact that, these columns, they rock and they can actually go up until large drift demands before they actually suffer axial failure. But of course, it's important to know that the energy dissipation is smaller, and you have so much of pinching behavior, which is actually a bit of a trade-off at the end of the day. So they are not so good, but they are not the worst of the lot. And then when we compare that with the retrofitted, you can actually see how well the retrofitted performs that compared to the shear critical and the bond critical components. So We used idea analysis using 44 ground motions to actually simulate to develop fragility functions for this component. And rather than basically adopt typical damage states, we are using 3 damage states, which is the immediate occupancy, life safety, and the collapse prevention coming from ASC 41 performance objectives. And of course, based on that, we developed those fragility functions for the buildings. And you can, so I will talk more about the collapse fragility curves. And the reason why I'm pointing to this is because of how relevant collapse is in terms of identifying buildings that needs to be prioritized for retrofit. So what the analysis actually shows is, depending on the analysis, depending on your criteria for deciding on which building to retrofit first, there's a likelihood of you actually favoring to retrofit a share-controlled column, a share-controlled building, before actually looking at the bond critical building, because the share-controlled building actually has the worst performance between the 3 considered variations. Then what does this mean? Conventional knowledge tends to point to the fact that if you have more splice length for a poorly confined column. So if I'm looking at a building from the 1960s, and I have one with the L over dB of 45, and I have one with the L over dB of 25, there's a likelihood that the one with 45 will perform better in terms of collapse. But what we don't tend to think about is that there's a transition from a bond controlled mechanism to a shear controlled mechanism, which then lowers the median collapse spectral acceleration. And then that results in these buildings having a lower collapse capacity despite having a larger splice length. And that is basically the influence of failure mode. And this is really not what people tend to think about, how the shift in failure mode would actually significantly influence the collapse fragility. And that is really part of what we were trying to really show with this current study. Unfortunately, time is far spent, so I think I could actually stop here. And I would like to just thank you for joining this seminar. I would like to take questions now. Thank you.
Perfect. Thank you very much. Again, my apologies for my voice. It's hay fever, hopefully. Thank you very much for a very interesting, let's say, seminar on different topics. It was, I think, a very good review for our students, because you talked about retrofitting, confinement, I don't know, modified Ibarra, Krovinkler's model, damage states, fragility curves. Like, it was a combination of lots of topics for our students. So I'm sure there will be some questions. As usual, feel free to unmute yourself or type it in the chat and I will read it aloud. Let's talk about the confinement and the retrofitting of the last building that you talked. Can you go to the slides? 2 forwards. Yes. Okay. Yeah. How did you do the retrofitting? Was it FRP or?
Oh, so for the archetypes?
Yes.
Oh, so for the archetypes, it was FRP retrofitted.
And it was just at the bond, or it was throughout the whole thing? So you were improving the flexural and shear, or just concentrating on the bond?
So for the numerical modeling?
Yes.
Yes. So the idea is, when you provide confinement to actually improve the bond, you're also improving the shear capacity as well. So it does a dual job of increasing your bond strength and increasing your shear capacity. So of course, what you then do is you go back to the failure mode classification approach to ensure that your shear capacity is really within the limits that you want it to be, such that you don't transition from a bond control to a flexure shear control type of stuff. So that is really the idea of designing the retrofit. And it was actually based on ACI 440. Yeah, so you basically use it at the top and bottom of the column.
Okay, and in the previous examples, you talked about FRC as well.
Yeah.
Can you talk a little bit more about that, and what was the difference of that FRC and this FRP? So that was like a concrete jacketing combined with some fibers?
Yes. So what happens here is you're actually having fibers So I think here they use some 10mm fibers, which are able to then increase the bond properties when you use them. So it has a higher concrete bond behavior compared to normal concrete, and that is actually what is used here. So what they did was they used jackhammer to really scrape out all the concrete around the splice region, and then they filled it up with this high performance fiber reinforced concrete, which then improves the bond behavior. So it's just jacketing versus wrapping. So for FRP, what you're doing is wrapping it, while for this, you're basically jacketing it. But the good thing about this ultra high performance fiber reinforced concrete is you're not increasing the area of the cross section. So typical jackets with normal concrete, you are increasing the area of the cross section. But with these ultra high performance, you are still keeping the cross sections the same. But of course, you're not using normal concrete. That is really the difference between the two.
Yes, and then you don't play with the mass, so the period of the structure doesn't change that much as well. So
exactly.
Very
so
safe.
you keep your stiffness the same, and which is pretty much why people tend to favor FRP over concrete jacketing, because with concrete jacketing, with increasing your concrete size, you're changing your stiffness, and that changes your period. So this helps you keep your period in check as well.
Yes. Again, as usual, if anyone has any question, please feel free to unmute yourself or type it in the chat. I will read it aloud. Yeah, always, whenever we talk about hysteresis and there's improvements in it, it makes me a little bit scared, because what about all of the models that we have been modeling for the last 20 years and we have missed these? Do you think it's still safe to trust those old models, or really we have to quickly remodel all of those, considering bits and pieces?
Oh, well, I think it depends on whether you're talking about research or engineering or practice. So in practice, what we actually have is a case whereby the seismic assessment guidelines keep on improving to really capture this new research. And of course, anybody that is looking at a building, maybe in 2022, would actually have a better grasp of the behavior compared to 20 years ago. But I mean, in terms of research, I mean, one is to basically adopt the state of the art when you're doing your research. While when you're doing engineering practice, you just need to use the state of the art in terms of seismic assessment guidelines. So I think it depends on the purpose. But I can't really say for sure if old works are bad. I think I should not be saying that.
Yeah. Anyone has any other question? Okay. I have a question about damage states.
Yeah.
How do you think the damage states are affected by considering or not considering the bond, the slip? Will it be a major issue, or?
So I think so. Let me go back to the slide. So let me go back to the slide to really talk about that, because that is actually a good question, especially if you're following, if you're basically developing fragility on functions. So when we look at this damage state here, it's really hard to really call. So if you're looking at what is currently used to really define damage states, when you look at what is happening at 1.5% drift, you could actually say the damage is minimal, or the damage is not so much. But in theory, it's experienced splice failure. It's experienced splice failure, and the residual capacity of this column is actually, I won't say negligible, but it's reduced by about 50%. So what you need to actually think about is it's not just what you see on the outside, but you have to have an idea of what is inside and what mechanism you're going to have. And that should actually inform how you predict the damage state. So the idea of actually trying to quantify damage state based on what you see on the outside, it's not exactly appropriate, especially when you're looking at older type structures. That is actually important. For older type structures, what you see on the outside is not exactly what is inside.
Yeah, fair enough. And I have a, not related to this topic, but where do you think AI will come helping us with the lab as well as nonlinear modeling. What do you think is the future?
Okay, what I think is the future for seismic assessment or for design, I think those are really too broad. That's a broad. So what do you mean in terms of design or in terms of seismic assessment?
If you want to explain both, that would be perfect. But I'm more toward the assessment side.
Oh, okay. So in terms of the assessment, I think part of what would be a challenge for artificial intelligence is the lack of significant data, which is really why a lot of older studies are not so appropriate, and we tend to really still go down to the mechanistic perspective, because we need that mechanistic perspective to be able to really capture this due to limited data. So if AI is really data driven, it's really hard for it to really work in the case whereby we only have 29 specimens for this. I don't really know how AI would actually work with 29 specimens. I mean, a friend of mine should have been on this call to answer that, but he's not here. But he would have actually told me that. But for now, I think some of this type of behavior, we really need to then you understand basically first principles, because part of what I've explained, the rocking behavior, the free body diagrams for the equilibrium, for the splice are actually first principles. So if AI can actually handle that, fine. But of course, I think we need to test probably 500 of these columns more before we can actually look at data-driven type of approaches to properly improve what we can do now. So what I've shown today can actually be improved. I'm not saying it's the best, it can actually be improved, but this is really based on the data that we have now. So anybody with more interest in testing can actually do this. And I should point out that it's still a big problem, because up until 2 weeks ago, I still spoke with someone who is actually handling an assessment of this type of bridges in Canada. So it's still a big problem.
Okay, so you think we're still far away from introducing AI in predicting the lab results and the experiments?
Not far away, but in lots of cases, we don't have the required amount of test data.
Okay. By the way, I forgot to mention this in your introduction. Congratulations on the 250K Marie Curie scholarship.
Thank you.
I think you're going to work on multi-hazard in reducing structural vulnerability again.
Yes.
Do you want to talk a little bit about that as well, or it's a secret? Yeah.
Well, it's not a secret. I'll be working with Professor Carmen. I think Carmen is on this call, and both of us will be looking at ways to for resilience enhancement for buildings under multi-hazard. So I won't really go into so much details because of time. But what I want to say is, people should be on the lookout for some of the interesting projects we'll be working on. Yeah.
Again, well done to you and Carmina. Congratulations on that, and we're very happy that you'll be staying with us for another 2.5 years, 3 years.
Yeah. Oh yeah, hopefully, yes. Yeah. So I think somebody asked the question in the chat.
Yes, I have a question regarding nonlinear modeling. If we apply FRP for column and we want to use lump plasticity model, which plastic hinge length model that we can use?
Yeah. So let me actually go back to the slide where I actually showed the relationship. So in here, although I don't go into details, but if you actually check the paper, in here there is already a plastic hinge model that is actually incorporated into this formulation. And that is actually how the model in itself calculates the required length to basically transfer that particular strain. Because don't forget, what you're dealing with here is actually strain penetration. So you are able to basically assume some form of average bond in the nonlinear and the linear phase, and that is incorporated into this model here for that case. However, if you're going through a different approach, the recommended approach is to use the Priestley equation of 0.044 FIDB, which also does a relatively good job. But I should point out that that formulation was actually developed using bars with a yield strength of 300 MPa. So when you're looking at some other type of yield strength, there's a possibility of your answer deviating from this. But I think we can spend another hour talking about that. because there are lots of studies on this already.
Okay, hope that answered your question. If there is no more question, I'll just share my screen for a second. So again, thank you very much for your time, and thank you for Dr. Eyitayo, who talked about the seismic assessment and nonlinear modeling of as-built, as well as the rehabilitated concrete structures with the bond deficiencies. We don't have any EPICentre seminar in the coming months because it's the exam month. But meanwhile, as part of the UNESCO chair project for EPICentre, we have the probabilistic risk assessment for disaster risk reduction, teaching on COPRA platform. So if you're interested, please visit EPICentre website and you can register. It's a 1-day, 2-hour online course on teaching you how to use COPRA. As usual, all of our recordings will be available on our YouTube channel as well as the EPICentre website. Again, I thank Tayo for his time and sharing such an interesting research with us. And again, congratulations on your Marie Curie.
Thank you.
Thank you very much, and we'll see you later.
Yeah.
See you. Bye.
Bye.